Alright, welcome to just another explanation of doing partial derivatives, and hopefully giving you a better explanation just of where everything's coming from and why we do what we do. So this is just 52 problem C. So you were supposed to do A and B for homework, and I didn't give you C because in case you needed this explanation, I wanted to go ahead and go over C again. So what we have is a function z that is defined by, it just tells us that we have a function that has two variables, x and y. Now both x and y are defined as r cosine theta and r sine theta. So we don't really know what z looks like. We just know that it's made up of two variables, x and y. All right, so what we want to do is we want to take the second partial derivative of z with respect to r and theta. And so we want to first take it with theta, and then we want to take it with r, based off of how it looks now. But again, due to Clairaut's theorem, we know that it doesn't matter the order in which I take it. I could take r first and then theta. And so that's what the one on the right represents, taking r first and then theta. The one on the left is taking theta first and then r, because again, in Leibniz notation, in the denominator, what's furthest to the right is the partial derivative you took care of first. So I'm just going to go ahead and do it. I'm going to take r first. So what I'm doing is I'm taking the partial derivative of our partial already of z with respect to r. So what I'm doing is I'm taking the derivative of our derivative, second derivative. And so when I do this, I'm going to take the partial derivative of, and I'm going to go ahead and do the partial z with respect to r. Now we've already done that, right? That comes from right here. So that's part A. So I'm going to go ahead and say, again, in order to get to r, I have to take my function, go through x, and then after going through x, I'm able to get to r, plus I go through z through y, and then go through y to get to r. And to clean that up, it's just, again, the partial of z with respect to r. We can go ahead and do the partial of x with respect to r, because that's r cosine theta, so that's just going to be cosine theta, plus the partial of z with respect to y, and then we can do the partial of y with respect to r. Let me make sure that you know that's r, and that's just going to be sine theta. All right, and again, you've already found that through A. So now what we want to do is we want to do the derivative of this. All right, so in order to do the derivative of this, we're going to be using the product rule. The reason why we're doing the product rule is because we have two functions times each other inside. All right, we have the partial of z with respect to x times cosine theta, and then we also have the partial of z with respect to y times sine theta. So because we have these two, because we have these products, these two functions multiplying each other, what we're going to have to do is do the product rule. So I'm going to take the derivative of the first times the second, plus the derivative of the second times the first. And then do the same thing. Take the derivative of the first times the second, plus the derivative of the second times the first. All right, and so there you see the product rule. Now, what we're going to have to do is I'm taking the derivative of the derivative here. All right, but there's a problem right there. All right, the reason why there's a problem right there, and let me just change up this, is because this is a function that can be defined by both x and y. So let me give you an example of that. Say you have z is equal to some function of x and y, which is exactly what we have. But this function could be something that looks like this: x squared plus 2xy plus y squared. Now if we took the partial of z with respect to r, right, then what we'd have to do, I'm sorry, the partial z with respect to x here, I would get 2x plus 2y. So when I do the partial z with respect to x, I still could get a function with both x and y variables. And because I can do that, if I wanted to say, hey, I want to go to, say, theta, all right, what I'd have to do is I'd have to go through the x and I'd still have to go through the y of our derivative already. All right, and so that's why we're having to do the chain rule again. Because this has x and y in it, I have to go through x and I have to go through y of my derivative. All right, so that's kind of an example. That's the reason why we're taking the chain rule. So let's go ahead and look at this. All right, we want to first take the partial derivative, and we're taking the partial of our derivative already, but the pathway that we want to go first is we want to go through x of this derivative, and then we'll get our x, and we want to go through x to get to our theta, all right, times cosine theta, plus, now again, we want to take, again, we're still having our function or our first partial derivative, all right, but now what we want to do is we want to go through y to get to theta, and then cosine theta. Because this function right here, oops, wrong thing. Because this function right here has both x and y, we have to traverse through x to get to theta and through y to get to theta of that function. All right, so that's why we had to use the chain rule, because that derivative could have both x and y. All right, and then we're going to do plus, we're going to do plus, and we're going to actually take the derivative there. We can actually do the partial derivative of cosine theta with respect to theta. The derivative of that is just going to be, derivative of cosine theta is negative sine theta, times the partial of z with respect to x. All right, so that's this first line right here. All right, so these first two terms give us all of that. All right, so now I'm going to do the last two terms, and that's going to be the second line. So now, again, we have that first partial derivative, in this case with respect to y. And again, we could have both x and y in this function. All right, in this partial derivative, we could have both x and y. So I'm going to first take my pathway through x of our derivative. And then once I go through x, I'll be able to go through to get to theta. All right, and then times sine theta. Plus, and again, now I went through x of our derivative, and now I want to go through y. So when I take the partial derivative with respect to y of our derivative, that will give me y, and then hopefully I go through y to get to theta, and again, that's going to be sine theta. Plus, I can do the derivative of that, the partial sine theta with respect to theta. That's just going to be cosine theta times the partial of z with respect to y. All right, now we're pretty much done. All right, all I'm going to do is I'm going to clean it up a little bit. I'm not going to clean it up all the way because that's just algebra. And, you know, I don't feel like I need to do the algebra with you because you're in Calc 3. But if you, again, want me to see the algebra, just ask me and I'll go ahead and I'll finish it all up with the algebra. But now I'm just going to clean up. So, no, I did not want to do that. All right, so now I'm going to go ahead and I'm going to take the partial derivative with respect to x of our partial derivative. That's going to give me the second partial derivative with respect to z and taking it to x with respect to x twice. All right. And now I can, so that gives me that. I can go ahead and do the partial of x with respect to theta. If we look up at the top, x is defined by r cosine theta. So if I take the derivative of r cosine theta with respect to theta, I'm going to get negative r sine theta. So then that gives me negative r sine theta. I'll highlight that for you. All right, and then times cosine theta. And so I can multiply that to finish this all off if I wanted to, like do the algebra. Now again, I'm taking another partial derivative of a partial derivative, so it's going to get me the second partial derivative. So I'm going to get the second partial derivative. A lot of times my partials look like 2. So I'm trying to fix that. So the second partial derivative of z, in this case, with respect to y and x. And so again, that comes from what I just highlighted in purple. And then times a partial y with respect to theta. I know that this comes from here. So what's the derivative of y with respect to theta? That's just r cosine theta. So I'm going to go ahead and denote that. R cosine theta. Alright, and that came from that. And then times cosine theta. So it's going to be r cosine squared theta. And then minus sine theta partial of z with respect to x. Alright, so again, that's that first line that's in blue. Plus, and now I'm going to do the second line in red. Again, I'm doing the partial derivative of a partial derivative, so I'm going to have the second partial derivative. Continue to use the same color. So I'm going to have the, get so mad when I use the wrong pen, and not the highlighter. So I'm going to have the second partial derivative again. Get so mad at myself. So I'm going to have the second partial derivative again. But with respect to x and, really with respect to y first and then x. Alright, and that's going to give me that notation. And then, again, I can do the partial of x with respect to theta. I've already done that up here. Alright, so that's just going to give me negative r sine theta again. So negative r sine theta times sine theta. And I'm just going to highlight where I got it from. And then, again, I'm taking another partial derivative of a partial derivative already. So right there. And then that's going to give me the second partial of z with respect to, whoa, I forgot my plus sign right here. Let me get rid of that real quick. So plus, so again, the second derivative of z with respect to y 2 times. And then I can, once again, take the derivative of partial y with respect to theta, and that's going to give me r cosine theta. Again, I've already done that. You can see it right above it. Alright, and then times cosine theta. Whoa, not times cosine theta. I looked at the wrong thing. Times sine theta. Alright, and again, it's really easy to make a mistake on this because there's so much going on. And then plus cosine theta partial of z with respect to y. Alright, and then that's it. The rest is just algebra, but hopefully you saw, why we're using the chain rule and why we have what we have. Alright, and so I'm going to just box up what the final answer would be. So like that, all of that right there would be part of your final answer. Alright. Hopefully this helped out. If not, again, ask me and I'll try to explain it a better